So far we've seen two mechanisms in this chapter. The first is electrophilic aromatic substitution, where we make something an amazing electrophile so that even the poor nucleophile benzene will react it. A second is where we add a really strong electron withdrawing group so that we pull a lot of electron density out of benzene, and we make it easier for a nucleophile to attack a leaving group on benzene. That's nucleophilic aromatic substitution. And now here we're going to see a third one. This one is called elimination addition. So each of those other two mechanisms had their own advantages. With electrophilic aromatic substitution, we were able to add electrophiles onto the ring. Anything that had a positive charge could go onto the benzene ring. For nucleophilic aromatic substitution, we were able to add nucleophiles onto the ring. Anything that had negative charge was put on the ring. But the one limitation that we saw was that the ring had to include a strong electron withdrawing group, usually a nitro group, in the para position. It would also work in the ortho position, but it's usually in the para position because there's less steric hindrance there. In the ortho positions, it's really close to the leaving group, so it's very crowded. So that is a limitation, having that electron withdrawing group. What if you don't have electron withdrawing group on the ring, but you still want to add a nucleophile? That's when you do elimination addition. So you'll recognize this reaction because you'll have a nucleophile that you're adding onto the benzene ring, but there's no electron withdrawing group. And to make this reaction happen, you really need a lot of heat. So if you take that electron withdrawing group off, it's harder, you don't form as stable of an intermediate, so you have to destabilize the molecule a whole bunch. And so you have to really heat the reaction mixture up. So that's the trade-off. Now, you end up eliminating this leaving group and then adding the nucleophile. So that's why it's called elimination addition. And what people noticed when they were doing experiments with this reaction is they noticed that if you put an isotope, if you put like a radioactive isotope of carbon here, you can track where that carbon goes. And in some molecules, the OH would go onto that same carbon, but in some, the OH would go right next door to the carbon that had the leaving group on it. The radioactive carbon that they can track was sometimes on the OH and sometimes next door to the OH. And so the hypothesis was that the intermediate, that the OH can attack either of these carbons, and so the intermediate must equalize those two carbons. And it does that, the hypothesis for doing that was that it forms what's called a benzyne intermediate, a benzene ring where one of the bonds is almost a triple bond. Okay, well, let's think about how that could happen. We have our benzene with our leaving group and no strong deactivators, or I should say no strong electron withdrawing groups on it. So we're going to just heat it up. We're not doing nucleophilic aromatic substitution, we're doing elimination addition. NaOH, that's an ionic compound. You have a metal and a nonmetal, so the OH by itself is going to have that negative charge. And the first step is to steal one of these hydrogens. So you end up doing a proton transfer. And the electrons from the hydrogen go onto that carbon. They stay in that same orbital that they were in, the sp2 orbital. So now we have this interesting intermediate. It's really unstable. And this is where you're able to form that intermediate that equalizes the two bonds, the bond, or the two carbons, the carbon that the bromine was attached to and the carbon next door. Those electrons push the leaving group off, and you form this very exotic benzyne intermediate. Remember that infix YN means that you have an alkyne, a triple bond. So you have a triple bond in benzene, so it's a benzyne intermediate. It's really unstable. At this point, another OH minus can come in, and it could attack either of the carbons in this triple bond. It could attack either of those with equal likelihood. And that's why people were observing that it was attacking either the same carbon that the bromine was on or one right next door to it. So if it attacks, let's say this top one, the electrons would go onto the neighboring carbon, and we have that unstable negative charge, and that's in the second step. Notice what we're adding, H3O+. That's really just there to provide a hydrogen. So that's an acid, and the negative charge there can stabilize itself by stealing this hydrogen. That's a proton transfer. The electrons here that were going to the hydrogen, those go onto the most electronegative thing nearby, the oxygen, and so you end up with your product. So notice the net effect is that you've just replaced the bromine with the OH. And you've done it not with the effect of a Meisenheimer complex, a resonance-stabilized Meisenheimer complex. You've done it with the effect of high temperature. So you form these really weird species that are high energy species, like this benzyne intermediate. And so that's elimination addition. So if you need to get a nucleophile on your benzene ring, and you don't have an electron withdrawing group, this is an option, this elimination addition.